can just do and collaborate easily. Okay, so this is where you need collaborators. Okay, this is where you need collaborators. So my first collaboration started with National Cheng Kung University in Taiwan. It was the nearest lab that can do the measurement nearest to Malaysia. Okay, so Taiwan was our first collaborator. It then led to collaboration with CAUS in Saudi, and then University of Southampton in the UK, and also collaborations with Australian. Okay, the Australian counterparts, three here. Prof Ho is from, and Prof Jagadish from Australian National University, and we also have Prof Judith from Macquarie University in Sydney. Okay, so all these collaborations started because of the struggles that we face in doing the research work, and it's been fruitful, alhamdulillah, and now we are building up the system in Malaysia, inshallah. Okay, so the outline for my talk today would just be to introduce the School of Physics, USM, introduce to the random laser itself, my main motivation in this work, the current findings that I can share, and the potential and future outlook that we have. Okay, so the School of Physics is located not very far from the Penang Bridge in Penang. It's on the island side, and actually the moment you go off the bridge, there is the road that goes exactly to the university. So it's like there is a direct link from the bridge. And then this would be one of the front gates of USM, and the School of Physics is an old building, but all School of Physics buildings throughout the world are old buildings because they have been there for a very long time. My office is just at the bottom here, at the end here. Okay, so that's the School of Physics. My work is mainly in NOR lab, so we have the Nano Optoelectronic Research Lab, whereby we have tools for deposition, surface morphology, structural, electrical and thermal measurements, as well as sample prep and treatment and some fabrication. Okay, so that's the NOR lab, and these are the NOR lab active members. It is currently led by Dr. Muhammad Marzaini, Muhammad Rashid. So if you want to make any form of measurements using the NOR lab facilities, the person you have to talk to is Dr. Muhammad Marzaini. Okay, and he will be able to assist you further. And these are all the active members, well, basically those who still have students working in the NOR lab. Okay, as you see, it's quite a male-dominated world, but we women don't actually give up, so we are rising, inshallah. So with that, I would like to introduce the concept of random lasers. It's a bit different from conventional lasers. So for those of you who are in the field of photonics or in the field of lasers, this may come as something a bit different from the usual concept of lasers. Okay, but I will explain a little bit. So the fundamental requirement of the lasers, you have to have three things. You have to have the pump, okay? So you have to have the source to actually give the photons. You have to have a gain medium. You have to have a medium that can amplify those photons, and you need a resonator for you to actually confine those photons before it actually comes out as a beam of light, okay? So you have to have basically something to make the photon. You have to have something that can amplify the photon. You have something that can keep the photon long enough for it to achieve a lot of gain before it actually goes out and becomes a beam. Okay, so that's the very layman basic explanation. Okay, so the source, the gain, and the resonators is something that is fundamental. It has to be there. Okay, now the reflectors here, in general conventional lasers, they are made by a pair of mirrors, so that you have to have physical mirrors, right? Okay, so you have to have physical mirrors at the end. Okay, M1, M2, right? That would reflect. So one of these mirrors would be partial. So R is less than 100% at one end. Okay, so that you can achieve some kind of output. So the photon would bouncing back and forth, back and forth, back and forth until the mirror cannot hold it anymore, so it will go out as a beam of laser, okay, laser light. So the difference between a random laser is that there is no physical cavity. There is no physical cavity. The cavity is actually made by an optical cavity. And how do you do that? By manipulating nanostructures. So this is what the interest of random laser is. How can you make a laser that does not rely on a cavity, just like the fundamental cavity that you have to have? So what is it that's giving this benefit, right? And it's actually the nanostructures itself. Because what you are manipulating is you are manipulating the refractive index. There is a refractive index change between your structure within the air, for example, or whatever medium you have in between. You must have that refractive index contrast. What would light do? What would light, photons, do when it encounters something with a change of refractive index? Anyone? It's a very fundamental physics question. What would happen to light the moment it encounters a change in refractive index? Anyone?
Probably.
Yes, exactly. It would definitely bend, right? So this bend is what we are manipulating. We are making the bend such that it would always bend inside. So what you get is that you create the nanostructures in a way that the light would be bending in a kind of circular or basically coming back to the same path. So we call this random walk. If you've heard about the random walk, okay, in semiconductors, this is something that you may have encountered before in semiconductor courses. So when you don't have any electric field, you can have random walks. And what we're trying to do is we're trying to manipulate not the random walk of electrons that we are familiar with, but the random walk of photons, right? So we want the photons to be able to be inside this particular gain medium long enough for it to actually achieve gain before it comes out. So the moment it comes out as a beam of photons. If it is not confined, if it cannot achieve gain, then it will just come out as spontaneous emission. You will not get lasing emission. But if you are able to manipulate the nanostructures so that it can confine the light, it can trap the light long enough in the nanostructure, you can get lasing to occur. Okay, and this is based on refractive index change, and there's another criterion called the Iofrigal criterion, which relates the size of your nanostructure with the wavelength of your laser. Okay, your laser emission, right? So the pumping source that you can have to achieve this can either be by optical or electrical pumping. Both are used in conventional lasers anyway. But for random lasers, in most cases, it's always by optical pumping, okay, which is by a light source. And by electrical pumping, you can also achieve that just by putting contacts directly to the sample, but this is very challenging. Therefore, there's very few reports on electrical-based random lasers because you already have the electric field that's already interfering with the actual nanostructures that you have, and they are semiconductors. Bear in mind, they are semiconductors, and semiconductors, they behave differently the moment they have this electric field. And if you need to have a lot of electric field, basically if you need to put in a lot of current, then it's even worse. Okay, so these are the challenges that is still faced by random lasers today. But although the random lasers are distinctively different from conventional lasers because it's multi-directional lasing, right? But the threshold behavior, so basically the lasing that you see see multiple lasing modes depending on the cavity that it formed in your semiconductor. For conventional laser, there is always just one mode output, right? Because only one mode can travel back and forth with the same phase, with the same exact wavelength. Okay, so but even though they are a bit different, the threshold behavior photon statistic, relaxation, oscillation, they are all similar to conventional lasers. You can use the same standard rate equation to describe lasing process. So these equations are still used for random lasing as well. Okay, so N here would be the number of excited molecules. So the rate of that is equals to the pump rate. Okay, and then you have the number of photons in laser modes, and you also have something called the spontaneous emission lifetime, okay, which is from the gain medium itself, either a dye or a semiconductor. It depends what your gain medium is. And beta here is actually the beta factor of random lasers. So this takes into account the number of lasing modes. And this tau C here, right? Now this is the mean value of cavity decay time. Now, because remember our cavity is not by mirrors, right? So our cavity is based on the photon diffusion equation, right? And the photon diffusion, by solving the diffusion equation, we can actually get tau C. Okay, right? We can actually get the mean value of the cavity decay time, which is dependent on L, and this L is actually the sample size. Okay, sample size, or if you are doing it by optical pumping, is the illumination area. Illumination area. Okay, so that's L. But it is also connected to the critical size for a sample to achieve lasing. Now this is back to the Eye-Rigel criterion, and the critical size for a sample to achieve lasing depends on the gain length as well as the transport mean free path. Now the gain length is just the path length when the intensity is amplified exponentially. So how long that is, right? And the transport mean free path, that's the average distance when the scattered light direction is randomized. So the moment it's no longer randomized, it's no longer the path that it will take. So this is where we can manipulate the most. And we can manipulate this using nanostructures. So that's the main ingredient in random lasing. Okay, so from these equations, it's basically your threshold, your laser process can be controlled by modifying the diffusion. Okay, and the diffusion of photons relies on this. So therefore, modifying these would also change the threshold as well as the modes of the random laser itself. Now, this is also dependent on, because we are depending on scattering. Remember, we are dealing with the change of refractive index. A lot of scattering happen. We want to achieve scattering that's inside and not going outside very quickly. So it depends on something called the scattering mean free path, which is actually, I would say, indirectly proportional to the scattering cross section. Okay, and the scattering cross section, for maximum scattering cross section, you need two things, right? You need to have the size of the scatterer, so the size of the nanoparticle has to be roughly the wavelength of the lasing. Okay, the wavelength, and there has to be a high ref index contrast. Okay, so the higher this contrast, the better the scattering cross-section is, right? So that's roughly a whole, I would say, the bundle regarding random lasing. Okay, so my main motivation, actually there's only two, of course, other than the scientific curiosity. That's actually the real motivation. Because imagine you have something, a semiconductor, that can become a laser without the need of an actual physical cavity that relies on nanostructures itself. It is modifying the way you can achieve lasing by just modifying nanostructures. So it's interesting on its own, but at the same time, we also have other motivation in terms of how can we make it useful, right? Okay, so my first motivation is to create speckle-free imaging. Now, the recent reports, this is in 2021, this year, okay, people have shown that they can achieve speckle-free imaging. So this is the image when they have a conventional laser. This is an image when they have a random laser. So you see speckle has been reduced, so you have very sharp images now, right? And there is also another report. So they use actual butterfly wings and moth to actually become the photonic structure. So it's not necessarily nanostructures that you create, but it can also come from biological structures as well. Okay, and these two show that speckle-free imaging can be produced using random lasers. Okay, so this is one of my motivation because two of these recent reports have one problem that they have to deal with. And that is, they are using dyes as gain medium. Dyes, of course, it can work to show the working principle, but in order for you to make it a working device, working with dye is not actually the best option. Number one is liquid-based, so you need to create some kind of capillary behavior as well. Number two, they bleach very easily. So the moment you have a high power, then it would degrade. The decay rate is very fast. Okay, so the degradation of the dye is an issue. Okay, so that is one motivation to replace the gain medium. Secondly, for identification of DNA, RNA binding and probing analytes. So this is something that there has been reports on. One example here that was published last year by the group in China, whereby they actually put in gold nanoparticles, and from the random lasing that they produce, they managed to actually use it to identify particular structure of cells. And another paper this year, just recently reported, whereby they used it to analyze. And as you see here, in both cases, they are using dyes. So they have to create some kind of capillary behavior and so on, because they have to replace this dye each time they have to make the measurement. So to me, two issues here. One, they need a fiber-based random laser. In both cases, they are using fibers. They're using optical fibers in both cases. Number two, they're using, again, dye as gain medium, because at the moment, it's more of proof of concept. Does it work? Can it work? Can it do it? So the proof of concept for now is already there. How can we then bring it further into making this much convenient measurement instead of having dyes, right? Now, the main issue is with dyes, it's much easier because, oh, sorry. Right. Okay, so the main issue with, okay, so that's the main issue with dyes. So what we wanted to look at is, can we have random lasing from solid state semiconductor gain medium? So a special focus that I will do today is be on zinc oxide, because this is something that we've been doing from the beginning. Okay, so the first issue that we have was, can we use simple synthesis of zinc oxide nanorods, which we can do in USM, on standard glass? Can it become a random laser or not? Or does it need sophisticated equipment? Do we need things like MOCVD to actually make it, right? So this was the first issue that we have. We created our zinc oxide nanorods, and I had to go ask around the whole of Malaysia if they have a setup. Unfortunately, there's no setup in Malaysia, so I had to go to Taiwan, which was the nearest, as I mentioned before. And they were with open arms. They said, yes, bring your sample, come and look at our setup, do one in USM later. So they were very welcoming. We are still collaborating until now, and we even created a MOU between us so that we can have more beneficial research activities to show our seriousness in this collaboration. So when we brought our samples, it was just a standard zinc oxide nanorod sample. I mean, USM has been doing this for almost 20 years, I think, doing a synthesis for nanostructures. It's just the application is different. And this time we're bringing this to the application of random lasers. So when we first measured, we saw that we see spontaneous emission, right? Kind of a peak, about 50 nanometer full width half maximum. So this is standard spontaneous emission that you see from any semiconductors. For zinc oxide, it's roughly around 380 nanometers. So this is something that's known. But what we realize is that as we increase the excitation power, the pump power, we realize that we start to see a peak. So lasing is starting to occur. And as we increase that pump power, yes, we see the modes coming. So 2 modes were observed for this particular sample. One mode is more superior than the other, but as you increase the power, this mode actually increases the intensity even more. But then there is a fighting of modes. So there are times when this mode dominate, there are times when this mode dominate, and this happens all the way until whatever high power that you go to. Okay, so what we observe is that there is a fighting of modes. So this is something that is not discussed very much in random lasers, but it answers the question. Yes, you can see random lasing in zinc oxide nanorod that are grown by a simple chemical bar deposition method on standard glass substrate. Okay, but I did not write here. The threshold for this, okay, to occur is actually at 0.5 megawatt per cm squared. So that's quite high. That's quite high. Okay, so we saw that we can achieve lasing. It brings us to the second issue. How can we reduce the threshold? Okay, so in order for it to become a beneficial device, the threshold has to go down. Okay, so we tried to, because it relies on scattering, as I mentioned just now, we tried to introduce more grain boundaries. So when we do polycrystalline nanorods, we introduce grain boundaries, and we were hoping that the introduction of grain boundaries will actually reduce the threshold. But no, the threshold went up even further, actually. So it did not work by increasing the grain boundaries. That's what we found out. It wasn't a positive effect that we thought we would have. However, we had some further information regarding, remember I mentioned about the fight of modes, right? Fighting for the same actual gain, okay? And we noticed that whenever we call this delta lambda, which is spacing, mode spacing. Whenever the mode spacing was more than, in our case, 2 nanometer, when it was more than 2 nanometer, the modes have equal access to the gain. So basically, they are almost 1. Actually, it's 1.0 something, but it's almost 1. Okay, the ratio of the peaks is almost 1. But if it's less than 2 nanometer, what we notice is that one mode would dominate than the other. Okay, so this is something that we observe as well. Okay, so these are all the lasing peaks. Each one of these are the lasing peaks taken at different areas of the sample. Although the same, I mean, it's roughly around the same wavelength. Okay, it's roughly around the same wavelength, a very small, tiny shift. But what we can show is that, number one, although the nanorods are not so uniform, of course, like if you see here, they're not uniform, right? And but overall, the overall effect, they don't really change the wavelength much. Okay, but of course, the cavity that is formed here, the cavity formed here, the cavity formed around here, the cavity formed around here, for example, would give 2 different lasing wavelengths. In some cases, you get 2 modes. In some cases, you get 1 mode. Okay, all right? So this is what we saw. Then we decided, okay, let's change a bit. Why don't we put ITO in between the zinc oxide and the glass? And what we notice, yes, there is lasing, which increasing excitation power, but we still see the fighting of modes, right? So initially there's only one mode that was dominating, and then suddenly we have the another two modes appearing. So these two modes appeared at higher pump power compared to this single mode. Okay, and so we notice when this happened, when these two modes start to get the gain, start to fight for the gain, we notice that we see a gain pinning effect. This means the intensity is at the same level. Okay, now gain pinning effect is not something that is observed in random lasing. It is something that is observed in conventional lasers. Yes. So we brought this issue to the Semiconductor Laser Conference, which was held in France, and it was not easy to get an answer as well, because it's not something that is observable in random lasers. But one way is that there is a fighting of the available gain. So the moment you increase the pump power, there are some other photons that are able to create the cavity or stay long enough to actually achieve some of the gain. And so you had to split some of the gain. Okay, all right, and so that's why some modes would appear and some modes will actually have a gain pinning kind of effect. And to reduce the threshold further, we decided, okay, let's dope the random laser. Doping is something that has been shown for semiconductors that it can reduce the threshold for lasers. Okay, so we decided to, okay, let's just try and dope with aluminium. That's the simplest doping or the most proven doping to happen in chemical bath deposition. That's why we choose aluminium. There is a bunch of metals that we can choose from actually. We were hoping for some plasmonic effects to occur, but we didn't see that. So what we saw is that yes, there is a certain doping concentration where the threshold is low, but the issue that we have that was highlighted by the reviewers of the paper, even though it was accepted, but the issue that is still there is that when we change the doping concentration, we change the morphology. You see that the size of this changes a lot. Okay, and by the time it reaches E, where the concentration is about 50 millimolar, then it becomes bigger, fatter, and more like the distribution is no longer as much, right? So there is an issue of, is it due to aluminium or is it due to the morphology? Because again, random lasing relies on the scattering element, right? So this was an open question at the time. So what we did was, okay, we have already tried doping. Can we actually do doping without changing the morphology much? So this was something that we, this paper is in press. It was just accepted last week, so it's not published yet. But I would just share with you what we've done. So my student here, Abdullah, have tried to create nanorods using a semi-autoclave kind of method. All right, and so what he did was he found out that doing this method, you can get roughly the same size or up to E. Okay, it's roughly the same size. There's not much changes in terms of the size of the diameter of the rods. Okay, so from that, we did the lasing measurements and we noticed that some measurements, some lasing are very superior compared to the rest, depending on the doping. So now, when we wrote the paper, the reviewers were happy that this is due to the doping itself. And so we don't have much counterback regarding the morphology. What we did saw, however, not just the lasing that's more superior or that happens with a very high spontaneous emission. This here, the spontaneous emission is very much suppressed. Okay, so not only that, we saw a change in wavelength. So basically, the random lasing shifts in terms of wavelength as we increase doping. Okay, so this is increasing our doping percentage, and then we see that the wavelength of the random laser actually shifts. Okay, and we notice that this shift is actually related to the photoluminescence that you see here. If you see here, there is a shift of this green peak going to here when it is rich with oxygen interstitial. Okay, so we notice that, all right, when you have low excess of oxygen or zinc, this is the kind of band gap that you see. But as you increase that concentration, you actually see something called band tail effect. Now, the band tail effect of doping actually brings down this. So this is why we see the shift of wavelength in our random laser. Okay, so the gain spectrum is narrowing, and we are seeing the change in wavelength with increasing doping. So this is what we have just reported, and this helps us to move further in this. Okay, so that's regarding zinc oxide so far. I would just touch a bit on other wide bandgap semiconductors that we've looked at. Now, this one is specifically done in Australia. So what we had was aluminium nitride rods that were grown on hexagonal boron nitride. Okay, now the issue is aluminum nitride is deep UV, so it's very hard to excite the deep UV. Therefore, it was not possible to do to actually make the aluminum nitride to become a gain medium. But what we did was we put in rhodamine 6G. So we had a dye to actually see if we can get lasing. Okay, if this aluminum nitride can become scatterless for random lasing to occur, and yes, we actually observed that. So there is a quenching of this with increasing pump power is what we observe. So this has been published last year. So this is the setup that was made together with Macquarie University because Australian National University had the facility for the fabrication, but for random laser measurement, we had to go to Macquarie University. And this was a collaboration with Prof. Judith Dawes. So what we notice is that for aluminum nitride, when we have hexaboron nitride as the layer, very thin layer, it's only like 10 nanometer or so, very thin. Okay, and what we notice is that that layer actually reduces the threshold compared to when we had nanocolumns, but it was just on sapphire. When the aluminum nitride were thin film, the threshold was even higher. You can still get random lasing, but the threshold was high. So it's apparent you need nano structure. It's apparent that you may actually need nano rods or nano columns, and it was also apparent that HBN played a particular specific role. And I think it's because hexaboron nitride does not absorb at 532, which was the pump source. So this means that there are more photons that are participating in the random lasing rather than in the absorption. So it's very important that you minimize the absorption of your substrate. Okay, so this is partly the issue with random lasers, and it's partly why you don't see random lasing occurring in all samples. Okay, it may be that in some samples that is absorbing much more, therefore the absorption is playing a much more role rather than the scattering effects. And we also notice that it has to be nanorods. Okay, when we looked into gallium nitride, this was also prepared by metal organic chemical vapor deposition, MOCVD, in ANU. And this is still under review, but I will share with you what we got. So these nano rods were self-organized, meaning that they had some kind of, they did not have any masking in order to make them. Okay, so what we noticed is that when we calculated the filling factor, which is the total rod area divided by the sample area, we see that there's a change in threshold energy density. Okay, so there is a specific number of rods that is involved that you need to actually get low threshold for random lasers to occur. And we also notice that the emission is everywhere. So this is the amount of angle that we change for our detector. So that's again showing that it's random lasing. If it was conventional lasing, Fabry-Perot, for example, then it would just emit one direction. It wouldn't emit multiple directions. So this is another proof of lasing. The reason why you see it going down is not because of the angle, but it's because we're using dye. So dye, they degrade. Again, as I mentioned, there is a problem of degradation of the dye. So we also noticed that if we put too much dye, so meaning that this is quite high, then the threshold is very high, but it's reduced very much whenever you actually put minimal amount, so just about cover the nanorods. So this is something that we also notice. The future outlook is, so again, I come back to my motivation of speckle-free imaging. Yes, we want to see if we can actually do this, right? So what we did is, we saw that there was, by a pioneer random laser, Professor Diedrich Wisma, who is pioneering in random lasers. He's been working this for the past 20 years or so. So he came out with a spectral super resolution spectroscopy using random lasers. But again, he was using dyes as well for the random laser to occur. So we proposed to him, why not we replace with our random laser and see if that actually created either the same effect or much better, right? So we established a new collaboration with Prof. Diedrich, and hopefully, inshallah, after all this MCO, we can follow up on this further. The second motivation is that I wanted to achieve identification of DNA RNA binding using random lasers. So to achieve this, I need to fix two problems, which is again using the dye as the gain medium. I need to replace it with the semiconductor, which is the zinc oxide that I have. Another thing is, or even gallium nitride or even aluminum nitride. The second thing is, it has to be fiber based. So what we did was we collaborated and we are hoping we can actually measure this sometime this year when the lab is open again. We have the setup in USM now. It's just a matter of aligning the setup, but we have all that we need. So inshallah, we are looking forward with the new collaborations that we have between Flat Silicates India and Berhad that's providing the fiber. They are making special fiber for us. And Dr. T.S. Wanzakia from USIM, who is working on random lasing in specifically for dopamine sensing detection. So she's working on the part of sensing with random lasers. So she has that expertise. So we're working together on that. I think she's the only one in Malaysia. Then we are also working with Uniten in the fiber component parts, inshallah. So we are hoping that this collaboration will be fruitful towards achieving our future goal, inshallah. So thank you very much. That's all from me. These are my research backbone who have helped me all the way until now. Even though it's the pandemic, we still meet online. So even with our collaborator in Taiwan, so our collaboration with Taiwan has always been fruitful up to this time. Okay, I'm open for any question and answer. Thank you very much. How do I switch?
Thank you, everyone. If you have any questions, you can just unmute yourself and ask away. I would like to remind everyone to please fill up the attendance form. If not, just, yeah, I have a question actually. So I was wondering, how do you actually set up, like pump your gain medium with the setup that you have in USM? I'm actually really curious.
Oh, okay.
You said you fabricate the nanorods on like a glass substrate, right? So how do you pump that?
Oh, kita letak je kat depan source tu je So this is the setup that we have. There is a bit more in terms of I kena letak beam splitter kat sini, but basically the sample will be around here, okay, vertically placed, and then the pump source will be pumping that, and then we will be detecting two things. We will be detecting from the pump source as well as from the sample. So you have to have a filter here as well. It's a very simple setup.
Oh, okay.
The issue mostly pump source tak ada. Itulah issue in most university kat Malaysia, because we don't have UV pump source. That is a lot. Itulah.
Okay. And then you mentioned about the gain pinning effect. I noticed that with conventional lasers, and it's very interesting to see that with random lasers as well.
Yes, we don't have an answer to that yet. even I asked this in the scientific committee, still they are saying that there's more work to understand this. They have to understand what the photon statistics is doing, which we don't actually look at yet. I think it's because it's not as established as normal lasers, so there are a lot of things that orang tak tengok lagi.
Okay. Yeah, betul lah tu sebab it's quite new, right? And
Yeah.
then you also mentioned about the diffusion,
Yeah, of
photonic
photons.
diffusion. Yeah, the diffusion of photons, which means that you could calculate the mean scattering of the path.
Yes.
Even though that you have like these random structures, but yet you still can calculate for the random path. I'm just like mind blown. So do you
Yeah, you
simulate that?
cannot, you don't know where the path is, but you can estimate how long it is.
Okay, so how long for it to scatter around, right?
Yes, how long, basically that would indicate the lifetime of it in a way. So you patah balik ke lifetime lah. How long does it live in there?
So there was a comment from the audience, the extra modes may originated from defect level below CB, extra electron transition.
Extra modes may originate from defect level. Yes. Yes, we can actually do the LTS. The answer is yes.
Do we have other questions from the audience?
But for defect level modes, they may be quite far away from the zinc oxide modes. So if the defect level modes are at 500, then to see lasing at 500 is very hard because it has to rely on the spontaneous emission punya background. Dia kena ada a pool of photons to work with. Dia tak boleh in thin air. So therefore, lasing would always happen within the zinc oxide range or whatever medium semiconductor that you have yang you jadikan gain medium tu lah. So it has to be like that. So I hope that answers Shahrul's question from Nadiah to Shahrul.
How high must your pump source be to do this?
Oh, quite high. Because as you see, the problem is that's the threshold lah kan. How much minimum power that you need. So as I mentioned just now, it can be as high as 1 megawatt per cm squared. It's quite high, right? And it can go down to even microjoules. But this again depends on how good of a medium that you create. So you can manipulate and test, then you know.
Okay, Dr. Maryam, Azif from BPM.
Yes.
Okay. Again, thanks for the interesting talk about your work. Okay. I am impressed. Just I have two concerns lah. No,
Okay.
probably I just curious to know more. First and foremost, your recent work on fiber, right? So you what is the wavelength that you use? Still UV?
Yes, we are planning to still use UV. That's why kena ada specific photonic punya fiber sebab dia kalau yang biasa tu tak tahan kan.
Yeah, what is the length of the fiber that you use?
Oh, at the moment it doesn't actually matter the length.
Okay, so
sebab sekarang ni just nak proof of principle dulu sebab tak ada recorded work on this yet.
Okay, so I think you are aware that using UV in silica glass fiber is not advisable.
Yes,
so
but
but it's okay.
Tengoklah, we are thinking of putting cladding outside.
Okay.
But I'm not sure if it will work. We will see. Baru try and error.
Okay, another question is if scientists know the behavior, the path, the light path behavior. I mean, if scientists know the light path behavior, even though it's random, I mean, if we can actually, scientists can actually pattern the nanoparticles or the nanostructure within that path. I mean, it may work, right?
Yes, exactly. I think so. So I think the issue here is engineering your nanostructures.
Yeah, so
like how random can the structure be to actually still create random laser, but it cannot be fully ordered. Otherwise, you will get very pero. So the issue is how random it can be random. Itu belum dijawab lagi.
Okay then. Okay, that's all. Thank you.
Thank you very much, Dr.
Okay,
Thanks a lot, Dr. Azim.
Waalaikumsalam, Dr. Nasir. Yes.
Okay. Thank you for your presentation. Very interesting, actually. But I come very late because I have some meeting with the internship students. So my question here, actually, I want to share idea with you. I don't know whether you mentioned this idea in your talk or not, because I come late. So if you use that nanorod on the metal deposit on the glass, like as aluminum or silver. So can this metal as a mirror to help you to get more intensity laser or random laser?
Okay. The issue of mirrors is it will create a Fabry-Pero effect. Then you may not get the random laser effect. That's one thing. But the introduction of metal may be a good thing, because if you get some plasmonic effect, then that can reduce your random lasing threshold much further. It has been shown to reduce quite a lot. So it will be awesome to combine that in a way that doesn't detrimental the random lasing behavior. Still, there is still a lot of engineering to work with that.
Because if your active medium is a very high gain curve, so definitely the single mirror very good benefit for you to get a more.
Yeah, but then that becomes a distributed feedback, right? So it's on the line between random laser and conventional laser, so we have to be a bit I mean we have to think about it a bit more.
Okay, thank you very much.
Thank you very much, Dr. Nasir, for your suggestion.
Dr. Maryam, we have one question from the audience from Yasmin. Hi, Dr. Maryam, great talk. Is there a possibility to make the setup more compact as a source for portable sensors?
Yes, there is, because it relies on nanostructures. So as you know, it's very small, very tiny. We have not downscale yet, so we are not sure. But we're hoping once we can identify the best structure, because sekarang ni dia random, meaning that when we do, I think we need MOCVD lah in this case to actually prove this point. So how random we can actually pattern the nanorods, for example. But this would require something like gallium nitride, because zinc oxide normally tak buat MOCVD. So we are working towards that, and we are hoping that flexible random lasers will be able to solve this problem. So if we are doing it in fiber, dia dah kecil kan, so this would solve this issue as well. We are hoping, but fiber comes with problems as well. They are mostly in the infrared punya range. Kita nak bring towards UV, I mean, as Dr. Aziz said, could be detrimental. Tapi we'll see how far we can go.
I think fiber is like another ecosystem for your work.
Yeah, exactly. So I need to collaborate with fiber people. That is why we collaborated with Uniten as well as Flexible.
And then Dr. Maryam, I was wondering, since you said that your structures are random, is it possible to reproduce your nanostructure, like the same randomization?
Yeah, that's another issue lah, because when you do simple synthesis, it's very hard to get the exact same kan. So that is an issue as well. But we are trying to actually, because what we've seen is that when we repeat, we tend to get roughly the same size, although they may not be roughly the same kedudukan, tapi the size is roughly the same. We're hoping that and so when we observe the lasing pun kita dapat lebih kurang wavelength yang sama. So it seems like the size of the rod affects more than the location of the rods. That's what we see currently lah. If you are able to make single X tall nanorods, will this improve the lasing? Single X tall? Macam mana tu, Jarum?
Single crystal.
Oh, single crystal, sorry. Okay, single crystal. If you are able to make single crystal nanorod. You mean in terms of crystallinity lah kan? Like for it to be kadar zinc oxide at 34.4 sahaja, macam tu ke? The answer is yes, it can improve lasing if that's what you are referring to. Crystallinity plays a role. We notice that polycrystalline teruk. Okay. I have a question. Why is ZNO? Oh, okay. Because kita nak tackle in the UV. So when you are things related to biomaterial are normally within the UV, satu. Yang keduanya is because zinc oxide is very senang nak synthesize. So to prove the point that lasing can work with these nanostructures using CBD method, which is still something quite recently. So 2016 onwards je ada yang by CBD ni. So we are kind of pioneering lah in that. So to prove that point, we chose zinc oxide. Another point is that for random lasing, the field of random lasing semua start dengan zinc oxide. So it's best to start with something that you know works before you move forward to the next material. That's just my kenapa I choose lah. I mean, Dr. Mahdi, who is also working on this in USM, is looking into silicon base. Tapi so far it's sangat susah. So we come back to zinc oxide juga lah.
Do we have other questions from the audience?
Dr. Fairuz excited tu, nampak kat gambar tadi.
Yeah, yes, Dr. Maryam, I'm here. So I see my picture. Thank you for the talk. It's fantastic.
Okay. So the controlling factors are the diameter and length. Yes, fabrication is the real focus. Yes, Dr. Sharon, correct. Exactly. Exactly. Fabrication is the real focus actually. Kena work dengan material engineering kot, but for now we can manage.
Okay, so I think we don't have any more questions from the audience. No more? Okay, so thank you so much, Dr. Wan Maryam. I think
Thank you very
everyone
much.
your talk. It was very enlightening in terms of random lasing, and it's very new. So it's I just really appreciate it. So thank you so much, and thank you to all the audience for joining us. Don't forget the attendance form. All right, see you everyone.